Boy, we have quite a crowd here tonight. This is great. Hi, I'm George Kraw. I'm your host for this evening. First off, I want to thank the wonderful the staff and the innovators from the UC SV Link Incubator. That was a wonderful program they put on, and I hope we can do that again soon. And wish them all great success in their projects. Tonight, we conclude the longest season of the Kraw Lecture Series, and I see a lot of familiar faces. Just curious, how many people have been here before, the group? That's great. Listen, we'll be starting again in October, so please be sure to pay attention to your email and put us down and invite your friends. And if you can't come, we'll be streaming the programs going forward too. So this year we're going to be ending with a bang. Well, sort of a cosmological bang. Hey, I don't write this. Actually, I have to give a shout out to my showrunner, Suze Halls. She does just a tremendous job. She's the one who really puts together all the programs and gets arranges for the speakers for us. But she, as she put down here, physicist Anthony Aguirre is going to take us deep into the past and challenge us with big questions about our future. Anthony is a rare and intriguing physicist in that he takes ideas beyond the concrete and immediate and helps us to think about them and about the cosmos, the universe, and the multiverse. Together with MIT physicist Max Tegmark, he co-founded the Foundational Questions Institute, and you may have noticed that he's on the current issue of the UC Santa Cruz magazine. He has a recent book out, Cosmological Koans, A Journey to the Heart of Physical Reality. So please welcome Anthony Aguirre.
Well, it's great to be here. And I want to thank also the Kraws and UC Santa Cruz for making this great lecture series possible. And to thank you for all coming out tonight. So where did it all come from? Where is it all going? It's a bit of an ambitious title, I have to admit, but I have two defenses to offer. First, I am a cosmologist, so this is my job. I'm supposed to think about the origin and evolution and nature of the universe. That's in the job description. But second, these are questions that people have been asking themselves and asking society and asking each other for a long time. So this is a painting painted by Gauguin in 1897, living in Tahiti, that he considers his masterwork, and he called it, "Where do we come from? What are we? Where are we going?" And this is something that we sort of have to ask ourselves as we go through life. And I think, as I said, people have been asking these questions for ages, probably since people were asking any questions. But there is something new that is possible in the last few decades. And there are two new things, I would say. One is that we can ask these questions about humanity as a whole. Humanity is a thing now. We aren't just a bunch of individuals. We aren't a bunch even of different societies. We can think of the human race as something that resides on the planet Earth as a whole, has a past, has a present, has a future that we can ask about and think about. And second, only in the last sort of few decades can we ask these questions in the context of a real understanding of what the universe is, what the largest scale context that we can think about is, how it works, how it originated, how it evolved, and where it's going cosmologically. So I'm going to ask these three questions and in turn, and I'm going to start with where do we come from, which I'll treat as a question in the cosmological sense of how did the matter and the order we observe in the universe arise. So let's start with the matter. Now, if you've been to a cosmology talk before, you will have seen a sort of cosmic census. And if you haven't, here it is. So this is in descending order of what fraction of the universe is made up in this sort of matter or energy. Those are the same thing, according to Einstein. The most Predominant component is vacuum energy. This is energy associated with empty space, a cosmological constant, dark energy. These are different names for the same thing that is pervading the universe and causing cosmological acceleration. This is a whole long story that I won't go into, but it's the most common stuff in the universe by mass. Then dark matter, the mysterious stuff that is binding together galaxies and clusters of galaxies but doesn't interact with normal matter. Then we have matter that we know and love, quarks that make up protons and neutrons, leptons that are electrons and neutrinos, photons, light that are pervading the universe. And finally, we've known that they were there, but measured gravitational waves directly. And there's a tiny little mixture of other exotica down at the bottom. So these are the kind of fundamental constituents of the universe. And the picture is that all these other things that we talk about, nucleons and atoms and black holes, dark matter halos, gas, molecules, galaxies, stars, planets, and so on, are things that are made up of these fundamental constituents. But I want to tell a slightly different story, a story that takes a little bit of the emphasis off of these fundamental constituents and places it more on the way in which they're combined. And I want to take that in two steps. The first, I want to talk about the question of where these fundamental constituents come from and reconfigure that a little bit by first saying there's one missing. There's a really big one missing. It's actually the biggest one is missing. The biggest one. Here it is, gravitational potential energy. That's weird. What is that? Well, if you take two massive objects and put them close to each other, they gravitate with each other. And if you actually weighed those two rocks close together, they would weigh a tiny, tiny, tiny little bit less than the two weighed individually. That's because the gravitational attraction between them represents an energy. That energy is negative, and so it actually contributes a little bit negatively to the mass of the two things close together. We don't notice this on a day-to-day basis. It's really tiny, but on a cosmological scale, it turns out to be incredibly important. And in fact, the gravitational potential energy is about the same, in fact, maybe exactly the same as all of the other ones combined. So another way to look at this is to say there's two types of energy in the universe. There's negative energy and there's positive energy. And a fascinating thing, a sort of amazing story that has come out of the physics of the very early universe is that you can actually create all of this stuff, all of the vacuum and dark matter and quarks and leptons and photons out of positive and negative energy, because all of these things can convert into each other at high enough energies, that is, at the energies that the very early universe had. So in some sense, the origin story of the universe in terms of these so-called fundamental constituents is that you start out with zero or very little energy, you split it up into some negative energy and some positive energy, you interconvert it into all these different things, and that's where the material constituents of the universe come from. So that's an amazing story that has to do with cosmological inflation, one of the things that I've studied throughout my career. It's not, though, the story that I'm going to tell today. What I'm instead going to say is that although I've called these fundamental constituents, they're not really, in the sense that, again, they're convertible into each other. They're just forms of positive and negative energy. Even those most fundamental things are structures that are generated through processes. So there was a process of inflation that split that energy into positive and negative, that turned it into all those different things. We have physical theories behind all of those things, but they were processes that unfolded in the history of the universe. So they're structures, in a sense, that have a history to them. And I'm going to tell you that everything else is too. Everything in the universe is a structure generated through processes that we have traced all the way back from the very early stages of the universe. Atoms, for example, this is my favorite picture of an atom. There it is in the middle. It's amazing, right? You can see one atom. It's an excited atom that's giving off radiation. They form, of course, all the time, but the particular atoms that our universe is made up of, mostly hydrogen, some helium, some mixture of other things, and then ones that are processed through stars, again, they have a history. The fact that the universe is mostly hydrogen, some helium, and so on, is a fact of how the history of the universe actually unfolded in detail. Those constituents, of course, made up things like molecules. Dark matter makes up dark matter halos. atomic gases make up, say, stars and things like that. There are lots of structures in the universe, from these large-scale ones like the stars, small-scale ones like molecules, much more complicated and sophisticated things like cells, animals, the biosphere of planets, amazing places like the Earth. Solar systems, this is this wonderful picture that Sandy showed in her Kraw lecture also, where Earth is this little dot up here. That's the Earth. Gives you a whole new perspective, doesn't it, to see it like that. Solar systems, on a larger scale, galaxies, so hundreds of billions of stars aggregated in a gravitationally bound group. Galaxies spread throughout the universe, and on the very largest scale, the universe as a whole. This is one of the amazing things that's happened in the last 20 years. We have a picture of the universe. There it is. So this is the so-called cosmic microwave background. This is a picture taken by the WMAP satellite. Actually, no, this is the Planck satellite. And what you're seeing there is, looking out from the center, you're seeing the sort of farthest distance that we can see in the observable universe. So the surface of the sphere is like the boundary of the observable universe, with us at the middle. We're looking back 13.8 billion years to see the density variations in the very, very early universe. So this is a baby picture of the universe, and that's the whole thing. That's the entire observable universe. For the first time, we know what it looks like. There it is. And like all of these other things, this is a structure that has been grown and has a history and is made of, in some sense, order and information and structure. So I keep saying this like it's a big deal, that they're made out of order and structure and information. What do I mean by that? What is information? What is order? What am I talking about when I say that things are made out of those, rather than saying they're made out of quarks or protons or atoms? And this is something that has come to fascinate me in recent years, how to think about what the sort of the ultimate constituents of the universe are, which I think are a little bit different, as I've said, from little particles. And to talk about what order and information are, I have to talk about what is entropy. Entropy is a word that you may have heard, but it's also a technical term. And it's a dangerous technical term, in a sense, that when professionals get together and talk about things and they bandy around the word entropy, they're almost always talking about different things, which makes it very confusing and very confused. But there are several technical definitions of entropy, and once professionals lay out those definitions, they sort of know what they're talking about. And I'm going to boil it down to two different notions of entropy that I think are sort of qualitatively different and worth discussing. Both of them, though, share this aspect that the meaning of high entropy is to say something is sort of more generic. Low entropy is more special or specific. So let's take two sort of examples, and they'll illuminate these two different notions of entropy. So one is your kitchen, right? If it's like mine, it's sometimes clean, sometimes less clean. And we know that there are a lot of different ways the kitchen can be. There are different places every plate and glass and piece of food can be. But there's a very sort of select group of those configurations that we call clean, a very much larger set of configurations we call messy. And if we just move things around, or if I let one of my kids make a meal, it will inevitably move into the messier and messier and messier ones, just because there are lots more of those. So there's a notion in which more messy is higher entropy, more orderly is lower entropy, and more messy is higher entropy in the sense that there are just many, many more ways that something can be messy than clean. And we can define this order, something called order, as a kind of lack of messiness. And this kind of coincides with our intuitive notion of the kitchen being orderly when it's clean and disorderly when it's not. There's another notion of entropy, which we could say is less specified or more specified. So if I take a string of bits, okay, there's 8 bits there, and suppose I don't know what any of them are. You just haven't told me, I haven't read the place where they're written down or on the computer chip or somewhere else. They're just a bunch of question marks. If I have no idea what they are, I would say that that's very unspecified, and I'll call that higher entropy. If, on the other hand, I know what several of the bits are, 0, 0, 1, and then the others are unspecified, that's a little bit more specified, that's lower entropy. And lowest entropy of all is if I know exactly what all 8 of those bits are. Okay? So from high to middle to low entropy, ordering them. Now this also enables the definition of information. So information is the sort of gap between the entropy that a system has and the entropy that it could have. So in this case, the gap between the entropy that it has and the entropy where you don't know anything, where they're all question marks. And so the one at the top has 0 bits of information, the one in the middle has 3 bits of information, and the one in the bottom has 8 bits of information. And this is exactly what we think of, and this is exactly what we mean when we say that some data stream or something has a certain amount of information. This is the technical definition of information invented by Claude Shannon and is used all over the place in information theory, in communications theory, in computation, and so on. So this is a very widespread definition of entropy. Now, these two notions of entropy, you can see, are qualitatively different, but they also have they also have a lot of overlap, and there's subtle connections between them. In fact, one of the things that I've been working on for the last couple of years is really better understanding exactly how to mathematically connect these two different notions of entropy in a more general way that kind of has both information and that notion of order that I talked about on the last slide, both as aspects of it. But for these purposes, we can just say that information/order is a kind of specificity to a physical system, and that there's an information content to a physical system related to how much you know or how much you've specified out of all the possible ways that system can be, the particular set of ways that you know that it is. Now, I've said that things in the physical world that have originated through this cosmological process have information and order associated with them. And we see that things in the world have structure. We see that the world that we're in is not ultimately messy. It's not a system in equilibrium. There's information content to all kinds of things in this room and in the world that we see. But this is a little bit of a mystery, actually, from what I've just said, for the following reason. Something that you may have heard about entropy, there's one really super important thing about entropy, which is that it increases. That is the second law of thermodynamics, probably one of the most fundamental physical laws of all, says that entropy does not decrease, and what that means is that order is not created, period. Order does not get created. There's also a aspect of the basic laws of physics that we know, Newton's laws, Maxwell's laws, the laws of quantum field theory, the standard model of particle physics. All of these basic laws of physics say that if you look at the state of a physical system, whatever that is defined by those laws, and evolve it, that information is preserved. Okay, so these are two very fundamental aspects of physics. Order is not created, information is preserved. They're in a little bit of tension with each other, so there are lots of interesting questions in the relation between these two. But the sort of core question that they raise is, if order is not created and information is preserved, it's not created either, then how do we have all this order that we have, right? The universe, this room is orderly. It hasn't descended into utter chaos. The world is orderly. Everything has a certain amount of order to it, but if order goes away, why is there any order around? Where does order actually come from? And the answer is pretty clear from the physics that it's always inherited from a larger system. That is, if you have a bin of Legos, which I've had just about this many, I'm a parent, it will not sort itself out, right? That bin will just stay there forever. You can shake it, you can move it around, you can get your kids to play with it, but it will not ever sort itself out. If you have a huge amount of energy, though, you can sort those Legos into a constituent thing. So you can give order to it. That is, you can make it a very special, among the very special set of configurations you would call sorted out by color, say. How is that possible? Lego, you're creating order. Well, the physics says that you aren't really creating order in just the Legos, you're creating order in the Legos, but creating disorder in the Lego plus parent system, right? So when you put those two things together, you can add a little bit of order to the Legos at the expense of a tired parent. That is, the parent has metabolized things, has digested some food, exhaled some carbon dioxide and so on. And so the Lego plus parent system has a higher entropy at the end than it did at the beginning, even though the Legos got more ordered. Okay, so we can create order at the expense of creating disorder elsewhere, always in a more than compensating amount so that the second law is satisfied. Same thing happens with the refrigerator. What does it do? It takes some warmish air in the refrigerator, some electricity, and crucially, a reservoir, a place to put air afterwards. It makes cold air inside the refrigerator and hot air that it puts out into the reservoir. Everybody should know that if you want to cool your house off, you can't just stick your refrigerator in the middle of it and hope for the best. It will make your room hotter. That's what the second law of thermodynamics tells you. You can cool off the interior, but there's going to be an expense with a larger system of refrigerator plus air plus reservoir where entropy is going to go up. So that's interesting. That's a nice explanation for why we can create order. There's always like a sort of waste, a dissipation that we have to take into account. But still, it pushes the question into a strange place that I like to call the great inheritance. So if you think about the kitchen, here's a kitchen, it stays orderly. How does it stay orderly? Well, somebody has to clean it, so it's got a cleaner. The cleaner can clean the kitchen. This is a monastery kitchen to go along with the Zen theme. And how does the cleaner keep doing that? They have to imbibe some low entropy, highly ordered substances like rice. That gives them a kind of boost of low entropy material so that the kitchen cleaner rice system can continue to increase entropy while the kitchen stays clean. Okay, but then at some point, that's going to stop working. You're going to run out of rice or run out of energy. So you have to include, where does the rice come from? Well, the rice comes from rice fields. The rice fields grow the rice from sunlight. Sunlight is a very low entropy source of energy that the rice plants can use to make nice low entropy rice that the person can grow to clean the kitchen. But where does that sunlight come from? It comes from the sun, of course, a star. The sun can exist because of that chemically simple, the hydrogen and helium gas that that the cosmos is endowed with. If all we had was iron, you couldn't fuse it to heavier elements and liberate energy from the sun. It's also related to the fact that the sun had to be created from clouds of gas that were relatively uniform. So if there wasn't sort of a uniformity, which turns out to be low entropy in gravity, then the sun wouldn't be able to form. And similarly, tracing that even to larger scales, we can go all the way back to the universe. Galaxies can form and exist in the way that they do because they were born from a very, very uniform, very, very chemically simple early state. And what's interesting about this is that although that early state of the universe seems unstructured and kind of boring and simple, and it is in a sense, it's very easily described, nonetheless, from the standpoint of information or order, it contains a tremendous amount of order. That is, in fact, the order that we inherit through galaxies and stars and rice paddies and rice and cooks and kitchens all the way down. So the fact that there is order in the universe still is due to this sort of amazing inheritance that we were bequeathed at the early stages of the universe of all of this order and information that we're sort of steadily making use of as the universe evolves, transforming it from one form into another. Now, that also leads to a question: where did that great inheritance come from? So I've said that, the universe started out with a bunch of energy, and it came from positive, negative energy, and there's a sort of story for how that turned into all the different forms of energy that we see. But I also told you now that it's endowed with this huge amount of order or information at the very beginning. Is there a story for where that came from? Well, I can tell you that I've been working on this question for quite a long time, and the answer is no. No, there's some interesting ways of thinking about this question, but I think there's nothing like the compelling story about how the matter came to be. And I think this is really one of the biggest unsolved, interesting, open questions in cosmology, because it is the ultimate origin question. Where did the information content, where did the order in the universe ultimately come from? We don't know. But what we've seen is that through the history of the universe, that endowment of order has generated ever more interesting, sophisticated structures through the galaxies, the stars, the planets, the biosphere, monastery cooks, and so on. So that brings us to what are we? What do we, life, things with agency, with intelligence sometimes, relate? How do we relate to this physical world? And this kind of comes into the question of information processing. So I told you that we start out, the universe started out with this low entropy, chemically simple, nearly uniform gas. And through all these processes, nucleosynthesis, structure formation, galaxy formation, stellar evolution, we ended up with things like enriched gas gathered in spheres that can give light to rice paddies and so on. So in this sense, there's an information processing. If you think of the order or information that the early universe had, it's been turned into different forms through these different physical processes. Information processing is very related, in a sense, to computation. If you ask what the definition of computation is, it's actually surprisingly hard to come up with a single definition of it. We have different models of computation. One is like the Turing machine, a little thing that reads tapes and so on. So there are all kinds of thought experiments that you can do with the nature of computation. But we sort of know when things are computing when they're things like this, like a microchip. We know that things are probably computing something sort of when they look like this. Brains definitely process information in some way. Exactly what way and exactly what the relation between what they're doing and what microchips are doing, I think, is a very fun and interesting question. Then there are other things like refrigerators or ATP synthase, the things that allow metabolism or the things that work on thermodynamics. They're doing information processing in the way that I described, or order processing. Are they doing computation? In a sense, with a sort of expansive definition of computation. And all of these concepts, the order, the information, the computation, are related in ways that are really just becoming clearer, I think, in the past few decades. There are all kinds of relations between them. One of the most fundamental was first enunciated by Landauer back in the 60s, I think, that points out that if you want to do some computation and you want to do it over and over again, you have to, crucially, erase bits. So if you want to do something over and over again, you have to complete the cycle and erase a bit. Erasing a bit is raising entropy. Remember, so destroying information is the same as raising entropy. So that's a little bit of energy dissipation. That's another related term. And what this says is that if I want to do computations, I have to it costs me heat. I have to create heat as connected to that computation. And this is something that we're facing now all the time. You turn on your laptop, you do some computations or watch a movie or whatever, it starts to get hot. We have data centers that are burning huge amounts of electricity. And that is due to this fundamental relation that as you do computation, you have to generate heat. And there's a basic limit to how much computation you can do with a certain amount of energy generation. So there are links between all of these things, and I'll come back to them a little bit quantitatively later. And from this standpoint, if we're thinking about the universe as in some sense a big information processing unit, then you can ask what are these things that are so dear to us and so familiar to us in these terms? And I'm not going to talk, each of these could be a long discussion and a fun one. So I'm just going to essentially give some definitions and leave it there, that we can think of life, in a sense, as a self-sustaining process that consumes information or order to preserve its structure and functioning. Now, no definition of life is perfect. There are lots of things to criticize about it. A star, for example, could be considered a little bit alive by this definition. But I think this is a crucial thing, that the second law of thermodynamics is constantly trying to drive systems to equilibrium. We resist that, not by contravening or like disobeying the second law, but by doing this trick of having an environment in which we can process information from one form, say chemical information in rice, into another form, ours, that keeps us at more or less the same entropy, keeps our structural information constant or more or less constant, and keeps us enduring. So there has been this chemical reaction that started, 3.8 billion years ago and has been going on ever since. We call it life, that is doing this, that is performing this function. And with life, I think a fundamentally new kind of aspect of the universe came to be, in that, if you talk about protons and electrons or gas clouds or stars, it's very not useful to talk about them in terms of goals or drives. You can sort of metaphorically, but these are just not physics sanctioned terms for electromagnetic fields and wave functions and things. You don't talk about them as having goals and drives. But it's really, really much easier and more efficient and more useful to talk about living beings as having goals and drives, or even computing systems, robots or machine learning systems or some other thing, having goals and drives rather than states and laws. You can describe those things perhaps in terms of states and laws, but you'll get nowhere in an explanation for why I took the particular route here that I took as shown to me by Google Maps. The way you would describe that whole process using Maxwell's equations would be just utterly pointless. Thinking about things in terms of I wanted to get to my destination, so I asked Google Maps and it decided here's his goal and here's the best way to do it and so on. That's the right way to describe that. And that's a new thing in the universe, I think, that comes about when you have living systems. Finally, very closely related, I think, is intelligence, another very difficult to describe or define thing, but a definition that I think has been getting more popular in some senses, that it is, in general, the ability to turn information into understanding and to accomplish goals. So intelligence is, in general, the ability to not just have agency and have goals and be able to be described in terms of goals and drives, but you can have different levels of the ability to do that. We certainly have that capability. We have an ability to accomplish our goals lots of the time, but lots of biological and some created physical systems have this ability too. Even the very simplest biological systems have a little measure of this intelligence in the sense that they clearly have goals and drives, and they're able to make choices in order to attain those goals. And this is a definition that can apply not just to biological systems, but to artificial computational systems, which certainly can be given goals and can pursue and achieve those goals at various different levels of capability. Those levels being steadily increasing in ways that are very interesting. So what I think is important about these is that they're sort of pointing out that we have, I should mention that that this organization that was mentioned in the beginning, the Foundational Questions Institute, one of the things that organization has been doing most in the last few years is thinking about exactly these questions. What is the relation between the fundamental physical laws that we know and love as physicists and sort of hard-nosed scientists at this fundamental physics level, and properties of these other systems like life, agents, intelligence? What kind of connections can you actually make between those, tracing their ability to process information to sort of turn information into understanding and to agency and to accomplish goals? How to fill in all those steps from the fundamental physics level to the level of accomplishing goals? There's so many holes. It's just a fascinating set of things to think about. So that's something that FQX has been doing quite a lot of. And from my standpoint, the way that I like to think about this is that there's a notion, I think, that has been built up over the years, which has been a very, very useful one, which is that there's the real fundamental physics description of reality, and that's the real one. And then there are all these other levels that are kind of approximations and so on that if you were really, really clever, you could just derive from the physics one. So physicists certainly carry around this kind of self-serving notion that physics is the ultimate thing and that everything else is kind of derivative of it. And I'd just like to say that I'm not of that camp, that I think that there are levels or descriptions of reality from this standpoint that all of which have in many senses equal validity, that there is this information preserving level. There's Maxwell's equations and Einstein's equations and the equations of quantum field theory. Then there's another level at which the laws of thermodynamics hold. And in some sense, you can derive those thermodynamic laws from the information preserving ones. But in some sense, they really do constitute a new description, a new sort of level of reality at which there are things like past and future come out of the thermodynamics. Cause and effect only happen at the thermodynamic level. There is no such thing as cause and effect at the information preserving level of Maxwell's equations. There's no such thing, for that matter, as past and future. There's no distinction between the past and future. That's only something that exists at the thermodynamic level. But it is a real thing. Similarly, the metabolic or computational level, where you can have rules that are processing information from one form to another, kind of set rules that that systems follow that are compatible with, right? They can't violate, but aren't the same as the fundamental, the information preserving level rules. It's a different set of rules. The biological level, where new considerations come in, evolution, is an explanation for many things. Evolution does not exist at the thermodynamic level or the information preserving level. Similarly, for the agential or intelligence level, I think it is useful to think of these different levels or descriptions of reality as different descriptions of the same reality that have relations between them, but not that there's a true one up at the top and a less and less true ones going toward the bottom. This is just, I think, an artifact of a useful process that has unfolded in physics, but I think is getting in the way of thinking about a lot of things clearly. So in this view, I think to sum up this sort of picture of reality, I think this leads to a notion in which things are made of information or order pretty much predominantly. They've got some energy and some associated with them, but that's not really what they're made of. They're made of that information. Information gets processed and changes form at all these different levels, none of them particularly privileged over the other ones. They're just different. And this is, I would say, a somewhat different point of view than a lot of physicists working today have. It's one that I've thought quite a bit about. I've even now, left one out. I've even now written a book. So this book came out a couple of weeks ago. It's called Cosmological Koans. And the very short story that I've tried to tell in the last half hour or so is told at much greater length here in the form of Zen koans that take place in the early 17th century in a trip between Italy and Japan. So it's a kind of strange package, but it will tell you, but I think it's fun, and it will tell you that same story that I tried to just tell about what the universe ultimately, in my eyes, is made of. So now I want to talk about not where we are, sort of as agents and creatures in biology, but where are we going? Sort of in the cosmological picture, where are we going? What long-term futures are available to us? And this requires prediction. So I want to talk a little bit about prediction. And predictions are really hard. The stock market, elections, weather, we don't know what's going to happen. Sometimes we're unpleasantly surprised. When it rains. But they're also easy, right? The sun comes up tomorrow. Things fall if we pick them up. I'm going to get hungry and sleepy later. So even complex biological systems are very predictable in certain ways. So we notice that predictions are hard when we can't make them. Other times we make them all the time. We make them constantly throughout the day, and we make them successfully, and we survive. We're amazing prediction machines that we've evolved to be. So whether predictions are hard or easy depends on what you're talking about. There are certain physical systems that are very easy to predict, in a sense. easy after hundreds of years of hard work in the physical sciences. For example, this is a catalog of solar eclipses from 2500 to 2600, right? We know to the second when these eclipses are occurring and how long they'll last and where exactly on Earth they'll be. I mean, this is really astonishing that we can do this, but it works. We saw one in 2017. It happened exactly when it was supposed to in exactly the right places. We could go there and see it. On the other hand, predictions of individual contingent events, I think, are probably literally impossible in the sense of, I think there is no sense in which, given everything that is possible to know about this room right now, that I can tell, or that anybody could tell in any meaningful way for sure what, say, you are going to have for breakfast tomorrow morning. For sure. That is the idea that we can determine exactly what's going to happen in the future for a complex system and an individual outcome, I think, is probably impossible. This is something that I'm actually working on now, sort of probing like whether it's truly fundamentally impossible or just really hard. On the other hand, probabilistic predictions of events like that are definitely possible. I mean, there aren't that many things you can eat for breakfast, and you're probably going to have probably the same thing that you had the day before. There are lots of things you won't have for breakfast, so you can assign probabilities to them, and those probabilities are very, very useful. And in fact, all the predictions we make are probabilities of this sort. One of my pet projects that I've been doing recently is something called Metaculus. It's a platform where you can ask questions and just ask lots of people to make predictions on it. So those predictions take the form of probabilities that something will happen, like will SpaceX land people on Mars prior to 2030? Probability of 42% right now. And so the way this works is that people make predictions. Those predictions are checked. You get points. And as you gather points, your predictions, if you gather lots of points, if you have a good track record, get weighted more and more in the aggregate prediction that the system makes of all the people who are making predictions. So this is just a good way to get accurate probabilistic predictions for things happening. And it works. So it's hard. There are all kinds of metrics, but the simplest and really pretty bad, admittedly, metric that I can tell you is that out of 220 questions since December 2017, 193 of them were on the correct side of 50%. So if you were just randomly guessing, you'd get kind of half of those. So the track record in various ways is pretty good. So this is very possible to do to make good probabilistic predictions. Modeling complex systems is really hard, but it's also possible. So we have systems that we'd really like to understand, economic systems, political ones, climate, weather. It's really, really hard to predict these things accurately, but we can predict them somewhat, weather for a few days, climate at some level, politics is very hard, economics at some level, but we can do it, and modeling is not always the same thing as predicting. Modeling can also tell us if we change something, then what will change in our model. And if our model is a good model of reality, that will give us a lot of insight into the system. So that we can do. And finally, analyzing trends and limits, like what is actually possible, is also very doable. So I want to apply some of these things to the long-term future. And the tricky thing about the long-term future is really a lot of it is technology. We don't know. Technology is very hard to predict. We don't know what's going to happen. And here's a fun question that I put on Metaculus. Will there be a total solar eclipse on June 25th, 2522, as predicted by NASA? Okay? So that eclipse is a sure thing in terms of astrophysics. 99.99% likely to happen. So why is the prediction only 87%? Because people are thinking in 500 years, the moon might not be there. Right? Not because it's going to get removed by some astrophysical thing, but because we might remove the moon to be used by something else, to use it for some other purpose. So that's surprising, that 13% probability, but 500 years is a really long time technologically, right? What was our technology like 500 years ago? It wasn't. So that makes it really hard, but one thing we can do is look at physics. What are the physical constraints on the very long-term future? And so I'll give some numbers here. And the crucial thing that you'll realize about these numbers is that they really don't make much of a limitation. Okay, so for example, The energy delivered by the sun is about 10 to the 14, so like 100 trillion terawatts, and a terawatt is then a trillion watts as well. 10 to the fourth terawatts to Earth. So that's a tremendous amount of energy, vastly, vastly more than we actually use in our civilization. If you just take, so the energy that we get from the sun, say, is created by nuclear fusion that liberates like 0.007 fraction of the matter into energy. If you turn all of the matter into energy, as we could with some future technology, you get 25 gigawatt hours per gram. Now the Moss Landing power plant, that's the biggest one in the area, is about a gigawatt. So you could run that power plant for a day on 1 gram of matter. Right? That's all it would take. Tremendous amount of energy just latent in ordinary matter if we could just liberate it. Of course, it's kind of good that we can't, right? It's kind of good that we can't, but hopefully by the time we figure out how to do that, we'll have settled our differences, let's say. Information and computation. So I said there was this hard limit to how much computation you could do for a certain amount of energy dissipation if you have irreversible computation. That turns out to be 10 to the 19 flops. So a flop is a floating point operation per second per watt. So 10 to the 19 flops is a lot. So the very fastest computers nowadays are sort of in the 10 to the 16 flop range, like aggregator for a large system of computers doing computation. So we use tremendously more than a watt of energy. That's how much we could get for a watt of energy. If you combine that with the last number, you get 10 to the 33 floating point operations per gram of stuff that we converted. That is just a tremendous amount of stuff. Similarly, the amount of storage that we could put in ordinary matter is between 1 and 100 zettabytes per gram. A zettabyte is 1,000 petabytes, which is 1,000 terabytes, so the numbers are getting really huge here. That's about the amount of information that has been stored by civilization up till now. That could fit into a gram of matter used maximally effectively. Okay. Now for comparison, the energy consumed by a human brain is about 100 watts running. You can compare that, say, to the 10 to the 14 watts delivered by the sun. So that's a lot of human-powered brains, used at maximal efficiency. If you think about, in the long-term future, converting matter into energy and energy into computation, well, the mass of Jupiter is 10 to the 30 grams, the mass of the Milky Way is 10 to the 44 grams. So if you're not limited by parochial thinking about being on Earth and doing the sorts of things we do now, but really thinking about the ultimate physical limits, they're very, very not restrictive. There's just a tremendous, tremendous amount of computation or human brains running or whatever we want to do that we could do. Some more limits: transmission speed, the speed of light. That's probably going to stick around. It's really annoying because stars are very far away. On the other hand, so stars are years away, even at that really high speed. Typical stars in the galaxy are millennia away. Other galaxies are ages and epochs, that is millions of years away. That's very frustrating. At the same time, the time that we have to play with potentially, the cosmological timescale, is 10 billion years or perhaps much, much more, so that the characteristic timescale of the universe is 10 billion years. So again, if we remove our thinking in terms of years and decades and things and think about cosmological timescales, these are very easy. So it's very easy on this sort of timescale to get to other galaxies if we just have the sort of technology. So the limits are very soft. Now I want to focus on some shorter term things in the future of computation. So these are graphs that you've undoubtedly seen before. This is Silicon Valley. Moore's law, in some sense, on the left. This is the performance of the top 500 computers added together in green. You can see this is the logarithmic plot on the left. So this is an exponential rise in computing power. It's been going on for like 40 years. I think not totally shown in here. And the efficiency of computation has been exponentially increasing as well. So two things to note about this. One, they're exponential. Two, they're slowing down. There's no doubt about that they're slowing down. But they're still, even a slowing down exponential is an exponential. And there's more computation coming, quantum computing, reversible computing, and other sorts of things that are much more energy efficient potentially, that don't dissipate energy. We don't know what those are going to look like. We have no clue whether they're going to have a Moore's law type of thing or not. But I think it's clear that given how useful computing is, the sort of know-how and resources are just going to keep getting put into making them more and more efficient and more powerful. And that brings us, I think, to the future of intelligence. And I want to address that in four somewhat startling, I think, at least they would have been to me 5 years ago, numbers. Here's the first one, 30 hours. That's how long it took the reinforcement learning system designed by Google's DeepMind to learn from scratch to be the best Go player or chess player on Earth. 30 hours of computation playing Go by itself. It learned what millennia of people had learned. So it was not only better than all the chess players, it was better than the AI researchers or chess game researchers that have ever existed. It just learned by itself 30 hours. Disquieting a little bit. 10 to the 18 flop per second is a reasonable estimate of, if you think that of the brain as a computer, the level of computation that it could be doing. That, coincidentally, is about the same amount of flop operations per second that the current self-reinforcement learning systems at DeepMind, not these, but the ones that learn to play StarCraft, are doing during their training sessions. So we're no longer at the point where the human brain is like vastly, vastly more powerful as a computer than the computers that are out there. We're now getting into the time where there's an actual competition. Third number, 1,000 employees at Google DeepMind. There are other major efforts, but DeepMind is one of the biggest. So machine learning and AI research has entered this sort of virtuous cycle where there are actual applications and money is just being poured in. So if the question is so to the degree that designing true artificial intelligence, the sort of thing that can actually compete with humans in their generality and range of sort of problem-solving capabilities, I sort of always thought of this as something very far off in the future, hundreds of years down the road or something. These numbers have made me rethink that a little bit. If you think about a problem that is unsolvable by about 1,000 really, really brilliant people working hard and getting paid lots of money to do it, not that many problems can stand up to that sort of capability. Finally, one more number from Mentaculus, 31% predicted to be the probability that there will be human-machine intelligence parity by 2040. It's not that long from now. And if I want a prediction about something, this is the best place I know to get it. So you can agree or disagree with this, but the track record is there. This is the best place I know to get it. So I think it's clear that maybe it's not 10 or 20 years from now, maybe it's 50 or maybe it's 100 years, but at some point there are going to be machines that have the same sort of intellectual firepower that humans now have. And I think the idea that the world is going to be the same after that simply doesn't hold water. That is going to be a phase transition in the history of life on Earth. And it's coming, I think, within our lifetimes, or our children's lifetimes, if not ours. And this is something that is worth doing a lot of thinking about. On the other hand, I do want to say that I wouldn't count out biology entirely. This is the cost per sequencing a genome. So that also has its own sort of version of Moore's law, at least for a while, although it's bottomed out a little bit since 2015. But a lot of the really exciting research on this is actually going on at UC Santa Cruz, these very cool nanopore techniques. So I think this might keep falling at some point. So the ability to harness genetic information and understand and manipulate it is rapidly growing. Whether it's as fast as machine learning is difficult to say, but it is, I think, going to be there in competition. Another thing worth thinking about is, these machine learning models do their thing by just lots of processing, tons and tons of processing, having that machine play Go against itself many, 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 many times. And there's a feeling in that community that lots of computation will sort of solve the problem of intelligence among some people. I think this is not necessarily the case. And if it were, the computation that you might have to be competing with is the computation that life has done through its evolution on Earth, sort of leading up to intelligent systems that are robust and live in the whole biosphere that they do, like of which we are one example. If you calculate the sort of number of computations that were done by Earth's biosphere through its history, 10 to the 47 is like a really, really, really large number. These exponential numbers can be kind of deceptive because it seems so innocent, 10 to the 47 up there. But this is just, there is no way that we're going to do that number of computations anytime in the future. This is like a world-spanning computation that's going on for billions of years at high efficiency. If it takes something like that to create artificial intelligence, we're simply not going to do it on any reasonable time scale, and we will be biological intelligences for a long time. So I think the question is open. I think it's most likely that there will be strong AI, but I think we should keep our minds open to the possibility that it may still be a lot harder than we think, and we should consider the sort of intelligence that is already here. So I want to talk a little bit about another question, which is, suppose we have new entities on Earth. If they're biological ones like us, I think we'll have a pretty good sense for what they're like. What if they're not? If we think about these sorts of entities, some of them, we really, really care about what their preferences are. Like these ones on the left, I care a lot about their preferences. I'll do pretty much whatever they want me to do. We care a lot about the preferences of this one. We sort of care about the preferences of this one, but not quite as much, right, for some reason. Unclear. We don't care that much in general for the preferences of this one or these almost at all. So there's a sense in which, why is that the case? Like what actually underlies that? Is it that some things are more complicated than others? Well, there are lots of complicated things we don't care about that much. It's because I think we feel like they have an experience of the world. They have an inner experience that is like something to be a boy or a dog or a horse or a cow or maybe an ant, and I don't know about a red blood cell. And because there is an experience, there can be a positive or negative experience, and there can be a moral importance to keeping the experience positive instead of negative. On the other hand, if we think of the first computer I had, it's much, much simpler than a red blood cell. A modern day robot, they seem to have sort of preferences, but I don't really care what they are. We don't have to really feel bad when people try to knock these things over on the videos. On the other hand, people care about the preferences of these little gizmos. And in the future, when DeepMind comes out with an assistant that seems very human-like, are we going to care about what its preferences are? Don't we need to know whether there is an inner light in that thing like there is in a puppy or a boy or probably a horse or a cow, or whether it's more like just a souped-up version of that? I think this is actually a crucial question in the very long term, because we need to know where the value lies. Is there value in the preferences of these things as opposed to these things? Because these things are coming. There's also a question of bigger systems. Apple, the state of California, we the people, humanity. We care about the preferences of these things in some sense, and often their preferences take precedence over ours, right? To what level should we? Is the state of California worth making happy for its own sake, or is it just a proxy for making the people that are part of the state happy? Different societies take different views of that, honestly, and I think that's an important question that we need to sort of contemplate. So I think in the future there can be a lot of value for humanity, but there are a lot of questions that we really, really need to be thinking about. What do we value, really, ultimately? And why do we value it? How do we compare or quantify that value if we have to make decisions that require that? Is there any value in an unconscious universe? This is a thought experiment I like to go through sometimes. What if we replace ourselves with descendants that aren't conscious in a way? Is that a universe that is worth having or not? Are there things that we value that don't have consciousness or sort of an inner moral light? What can we do now that our descendants will thank us for? And how can we know? So like 500,000 years ago, the human population was down to like 1,000, according to some studies. According to some, even like 40 pairs of humans. I'm really glad they made it, right? Aren't you? It's hard for them to know what would have happened in the future. It's hard for us to really thank them in earnest. So what can we do now that our descendants will thank us for? And how are we going to know the valence of our actions? It's a hard question. What are we going to clearly regret a long time from now? I suspect killing off all these different species with the tremendous amount of information, that the genetic information that they carry, is probably the primary one. And when you look at that time scale, you realize, my God, what we're throwing away just willy-nilly, it's very upsetting. And how can we best use our resources to improve the current and future world? So these are questions that I think should be on a lot of our minds, and I think they're getting to be more and more on people's minds. So there's been a sort of proliferation, I think, in the recent years of organizations and projects thinking about this fact that the character of life on Earth is rapidly changing. The fundamental character, whether it's genetic or artificial intelligence or what, we are in a very crucial time period, I think, where the long-term existence of humanity and the long-term future of humanity really is at stake in the next coming decades, maybe 100 years. And we have organizations like the Open Philanthropy Project, the Templeton Foundation, the Gates Foundation, philanthropic organizations, nonprofits like the Future of Life Institute that I'm a part of, and others, and academic centers that are putting a lot of work into this, the Center for the Study of Existential Risk, Future of Humanity Institute, and I hope to larger and larger degree, the UC Earth Futures Institute. I think it's vitally important that there are organizations, including on the academic side, who are really grappling with, at a real level, this fundamental change that's coming over large timescales, trying to do predictions about it, trying to understand what we can do now in this wider context. So I'm very excited about this, and I'm excited, and I'm optimistic, I think, that although the problems are incredibly severe and incredibly scary in a lot of ways when you think about them, that humanity also is an agent. It has over millennia worked very hard and succeeded in making things better for itself. And I think there is a real possibility that we are going to get our act together and think clearly about these questions and make good choices. And I just want to leave with one of my favorite quotes from early 20th century philosophy Henri Bergson, that people do not sufficiently realize that their future is in their own hands. Theirs is the task of determining, first of all, whether they want to go on living or not. This is true of our species. Theirs is the responsibility then for deciding if they want merely to live or intend to make just the extra effort required for fulfilling even on their refractory planet, that's a great phrase, the essential function of the universe, which is a machine for the making of gods. So let's keep the machine running. Thank you. I think we have so the questions have to go through the microphone. So the microphone wielder is all powerful. Yeah.
So you're obviously not your traditional caricature of a physicist, and for that I thank you very much. Harkening back to, my wife's a physicist, she's hitting me. Something you mentioned, but I'd like to ask if you'd be willing to elaborate on your definition of life earlier, allowed for the possibility of non-biologic life, and you sort of touched on that later on. I was wondering if you could amplify on the notion of non-biologic life and its role going forward.
Yeah, so when we talk about life, we often have this definition that includes things like reproduction and evolution and things like that, and I think that's fine. I'm arguing about definitions is not that exciting, but arguing about what is the or discussing what is the very, very interesting thing that life does, I think is worthwhile. And to me, the very, very interesting thing that life does is this amazing ability to add this new sort of level of description or new level of reality on top of that, those kind of inexorable grinding laws of physics that just roll along. There's now this level where life, although this incredibly delicate thing, is also robust against the action that those fundamental laws would normally make, which is to make the order and the information go away. So that second law of thermodynamics, I think, is so fundamental. It's a part of every physical process, and I think it is the right way to think about it, to say that life is resisting that in a way. It has this homeostasis, this kind of organizational form that it is trying to maintain in spite of that tendency, that second law. And I think that's what makes the sort of line, when you see some physical system die, that abruptness of the transition is that suddenly that ability to sort of fight against the second law locally while observing it globally just suddenly fails, right? And you see that thing which had this capability suddenly turn into kind of inert matter. It's a very abrupt and kind of clear and meaningful thing to see that process stop. So I think if in the future we have systems that can still perform that same function, the robots and things that we have now do not do this, right? They're just subject to the second law. They decay sort of inexorably. We can keep them going by feeding them electricity, and so they sort of maintain themselves in that way. But they don't do it in the same way as a biological system. They just run down and we have to fix them. If we come to the point where our machines are so sophisticated that they are essentially doing the same thing, they're playing with the fundamental laws of physics in the same way to maintain themselves, to metabolize, then I would call them life at that point, even if their form is very different, and even if they didn't reproduce or evolve.
Thank you for the presentation. I have a couple questions. One is regarding your description of information. I know when Shannon came out with his law, he was told by von Neumann, call it entropy, because nobody will understand you, and you'll always be right. And that's a really hotly debated topic, I know, in physics. Is Shannon entropy the same thing as Clausius's entropy? And that's something that, I mean, we could talk offline probably for hours on that, because I know not everybody says that those are equivalent. But I also want to ask you about order, because the example with the Legos, that's a really large order of, yes, putting the red ones and the blue ones, but by increasing the temperature just a fraction of a degree, you're by orders of magnitude increasing the entropy more than the order. So the concept of order is a human subjective concept. So how do you relate that to entropy? Is that just like a metaphorical description, or is it actually entropy that you're referring to in the Lego case, for instance?
Yeah. So this is, I agree, a fascinating topic, and as I said, the last few years of my life with another professor and a postdoc at UC Santa Cruz, this is exactly what we've been working on. What is the right way to think about entropy that connects both with the sort of Shannon definition, or in physics, the Gibbs or von Neumann definitions, which are sort of the equivalent, but also with the notion of order, which is kind of the way Clausius or Boltzmann especially thought about entropy. And I think we have at the risk of sounding slightly grandiose, I think we have an answer to that. Like, I think there really is a nice way to see what the relation between those, and to define entropy in a way that sort of has both of those things as different limits of the same notion of entropy. So this is work that I'm actually super excited about, and hope that more people will, especially physicists, will read and understand, because it's one of those things where it's been so confusing for so long, at least to me personally, that to actually make some headway and feel like, yeah, that makes sense, and now I see what the relation between these things is, feels really, really good. So I've really enjoyed that process, and I think there are good ways of thinking about it that are very difficult to convey, in a talk like this. But I can send you a paper, and we can discuss more.
Around 2 million years ago, a genetic mutation occurred in monkeys, which increased their size of brain. And whatever we see around here is a result of that genetic mutation. Because they started making things and their brain size increased, and now we are here discussing things. Otherwise, if we can work out how that genetic mutation occurred, at least we will know how we came into being. And then we can think about universe and other things, how they came. That's what I think, and that should be simple, isn't it?
This is actually being worked on. I know I've talked with David Hausler at UCSC, and this is the very question he's working on. What are the specific genetic changes that have occurred in primate evolution that seem to distinguish us? And there are some that have been identified. So this is, I think that is a question that we will know the answer to, like what specifically happened in the history of the, Homo sapiens genome. But I think there's a bigger question that is a question that fascinates me is how the genome has evolved such that you can make a mutation like this random chance thing, and often it will be deleterious and the thing will just die. But surprisingly often, it will lead to a viable organism. So our genome is this very amazing sort of, I think, computation that's going on that is unlike any sort of computer that we run now. You change one line in a computer code and the chance of it working is like almost zero, right? Whereas in the genome, it's incredibly robust. So people are now admitting to themselves that there are lots of wrong lines of computer code, but they still work. This can occasionally happen, but in general, computer code is very fragile, but the genome is not. We smash it together like 50-50, and it still works most of the time, right? In sexual reproduction, and there are parts of the genome that are clearly sort of hard-coded in to almost not change at all, like basic enzymes, and then other parts that are made to vary quite a bit to provide lots of variation. So there's clearly the ability to evolve and vary has evolved as well. How many levels deep that goes, I think, is an interesting question. So I think we're just starting to probe kind of the depth and complexity of what evolution has created in life now. And I think we will get some low-hanging fruit answers, like what specific genes, changed in the history of Homo sapiens. But the bigger question of why changes like that can just scale up intelligence, I think, will be a long time coming.
There's a question in the far corner.
Yeah, thank you very much. I have a list here of about 25 questions.
Love it.
So I'm afraid you've increased my entropy substantially. So I'll just pick out one of them. Do you believe that physics has anything to say about free will or about determinism in the universe?
Yeah, so those are two different questions, I think. I think physics certainly has something to say about determinism, which is that there is not determinism, and there is. So there is a level of description at which the physics is deterministic. So there's a wave function of some physical system, and that has deterministic laws that govern how it evolves. But when you ask what that wave function evolves into in terms of, like, if we take the wave function of this room, and the laws of physics say that there's a single wave function 10 minutes from now that evolves into, if you were to know the wave function of the room. But if you ask what room does that correspond to, there's not a single answer. There are lots of different rooms that are in that one wave function. And so at the level of a room, the room now maps into many rooms in the future, not one. And so at one level, physics is deterministic, but at another level, it's just not. There's a one-to-many mapping between the present and the future. And so in the sense that I think there's no way that you can say the room as we experience it, full of people and chairs and things, evolves into a single room in the future full of people and chairs. It evolves into many different ones. I think that's just clear in the physics. So at that level, I think determinism is and isn't true. Now, whether that's sufficient for there to be free will, I think really depends on what you mean by free will. And this is another question like entropy that you can talk about a lot and always be right and wrong. So to me, I think of free will as a set of possible things that a system might have. Like, if you feel like you can make a decision like free of coercion or like people, or some force forcing you to make a certain decision, that feels kind of free. If you feel like you have like you could have made a different choice, that feels free. If you feel like you're actually deciding, not like the result was a foregone conclusion, you feel free. So I think there are different aspects of free will that you can ask, or whether your prediction can be whether your decision can be predicted by some other agent is another thing that determines sort of whether you would feel free or not. So I think there are different aspects you can break free will down into, and you can ask questions about whether those aspects pertain in our world. And I think some of them do, and maybe some of them don't. So I don't think there's such thing as I don't think you could get two people to define free will in the same way, probably, if you worked really hard. But I think you could break down some things that people would say are aspects of free will and check whether we have those or not. And some of them I think we do.
If you look at the history of the Earth, and especially life on the Earth, it's a story of increasing complexity, and you could think of it as decreasing entropy. Of course, the Earth is not a closed system. The sun is shining on it. But I'm wondering, has there anybody studied the conditions under which this anomalous thing can happen? Order can seemingly increase in some local place. And are there any laws about how quickly it might happen, or how can you predict where in the universe this kind of phenomenon might be going on, and how quickly it could be expected to happen?
Yeah, I don't. So there's two things baked into there: complexity and order, which I think also may be related. But I think unlike order and information, I think we don't have a good definition of complexity, at least not one that I know. And we sort of know it when we see it. It's like clear that there are more complex things on Earth than there used to be. But it's very, very hard to come up with exactly what that means in a way that we can quantify it or kind of trade it off against something else in the way that we can with order or information. So I think I don't know. I think we can put our hand or kind of wrap our heads around order generating processes, and some of them can be very simple ones like stars that are generating order in some way, or like chemical reactions that are generating order. What complexity means and how it gets generated and whether we can predict whether it gets generated and how fast. I think those are really fascinating questions, but I think we're just like even more at the beginning with those questions than with many others. So I don't know. It's the short answer.
Okay, so I am not a scientist. I haven't had any science outside of 2 years in high school. That was almost 50 years ago. I get depressed when I read about climate change, global warming. So what you said seemed to be a little bit more positive, that maybe that could be halted. But what I want you to explain is the essential function of the universe, which is a machine for the making of gods. What did he mean by that?
I think what Bergson meant by it was that we have this sort of sense of this mechanistic universe that has laws and it just kind of grinds away. It's a machine. And yet within that machine, we seem to have things that are not machines, that are operating at a different level, that have wants and desires and morals and intelligence and thoughts, and are just all sorts of entities that aren't anywhere in those like laws that are grinding the machine along. So there is at one level these information preserving laws of physics grinding along, but there is at an equally real, I feel, level the generation of new levels of reality, including morals and moral progress and society and social progress and these things that we really enjoy. So I think that is what he is really talking about, not literal gods, but things that have a true power of creativity and thought, that such that you have to describe the universe in a totally different way once those things come into existence. And I think life is at some level like that, but where life is ultimately going to go, I think is what he was talking about there. What our long future descendants with vastly greater capabilities and presumably vastly greater complexity, vastly greater ability to contemplate, to grapple with moral issues, to create ever more sophisticated societal and social and intellectual structures, what will they look like? And that's how I read it. I think it's going back there. Next.
Hi. So, is water native to Earth, or it came from outside? I mean, other planets have water too, but not such humongous quantity. So, was water there when the Earth was being formed? Or,
Yeah, this is not my expertise, but my understanding is that it was bombardment by comets after the early, like, hot fireball phase of the Earth.
Thank you.
Thank you, Professor. Excellent presentation. Going back to your technological outlook into the future, you're indicating that there's like an inevitability of biological intelligence creating technology evolving into AI, and then it takes Moore's law a few decades or centuries to be the dominant intelligence in a region of the universe. If one applies that, then the question is, where are they with respect to kind of opening the question, how unique is our position in the universe in that, well, if that evolution would be some sort of natural law, Fermi's paradox, wouldn't they have been at our place like billions of years ago?
Yeah, so I think this question of, given the sort of numbers that I indicated, if you have high technology going at a significant fraction of the speed of light, it just doesn't take that long on a galactic or cosmological timescale to spread very far. So why hasn't that happened? You know, that is such an interesting and fundamental question. I've discovered that in my own mind, I've kind of just evolved to this default position that there is some incredibly highly improbable event that happened, probably in my thinking at the origin of life, where I wouldn't want to make a strong argument for this, but I feel like my thinking has evolved to the point where the origin of life is just incredibly, incredibly, incredibly rare. And that's not very hard to believe in the sense that there's when numbers get small because they're combinatoric, you're multiplying lots of small numbers together, they can get really, really, really small. And even when you think about the number of planets and oceans and things that are out there, they're easily dwarfed by some large combinatoric factor like that. So I think it's actually quite plausible, and analyses that are sort of more carefully done of Fermi's paradox and Drake's equations, I think, bear this out, that we are the origin of life in the observable universe. This is it. And that's so heavy, if you take that seriously, that's a heavy burden to bear, right? There's no backup plan B, other team ready to take over, like making use out of the universe if we screw it up. So if it's both reassuring and scary to think that there are other intelligences and life out there, but it's also sort of, I think, inspiring and terrifying to think that we're the only ones. So either possibility is heavy, I think. But personally, I'm sort of leaning in that direction now, and that's one answer. If you don't look at it that way, then I think it gets very confusing very quickly. Indeed, where are they?
In your talk, you referred to a point where Homo sapiens almost disappeared. There were maybe 1,000 or 100 Homo sapiens on Earth. Can you say more about that? I hadn't heard that before.
I can't really, so that's just something. I was starting to read some of the papers actually yesterday because I got interested in that, but I didn't get through them enough to. But there are some scholarly articles just looking at the genetic lack of diversity, as humans go back, and there's a theory, I think you would call it, or an idea that the Toba supervolcano, which I think was 700,000 years ago, nearly wiped humanity out, and there are other potential bottlenecks. So I wouldn't take this to the bank, but you can look it up, or I can send you some things that I found. So I don't know how secure a footing that is, but it's interesting to contemplate. I think just if nothing else is a metaphor for where we are now, that it's quite possible for something with a huge future to go through a very dangerous time, and it just may or may not make it through, and we may be in that situation now.
Thank you.
Yes. So I've been given the secret code word for thanking you all for coming. This has been a great discussion. I've really enjoyed it. The question and answer is always the most fun part, I think. And there's time for a little more of that. Stick around for coffee and discussion afterwards. So thanks again for coming.